Hello everybody. In this video we are going to be looking at the solutions to the Honors Magnetism homework problems 6 through 10. Well, let's get started with problem 6. We have a proton moving at a speed of 3.0 times 10 to the 4th meters per second, entering a magnetic field of 0.55 Tesla as shown in the diagram. They want us to find the direction and the magnitude of the magnetic force on the proton. So let's look at the magnitude of the force first. I'm given the charge of the proton, which is 1.6 times 10 to the minus 19th coulombs. I'm given the velocity of the proton at 3.0 times 10 to the 4th meters per second. I'm given the magnitude of the magnetic field, 0.55 Tesla, and I'm being asked to find the force. To find the force, I know I need to use F equals QVB. I plug my known values into the equation, and I'm going to get a force of 2.6 times 10 to the minus 15th newtons. That's the magnitude of the force. Now let's take a look at the direction of the force. I know that my magnetic field, B, which is represented by B here, is shown as these dots. And these dots are telling me that the magnetic field is oriented in the positive Z axis. In other words, it's coming out of the screen, coming toward me. And I know that the velocity is in the negative Y direction. So if I use my right hand, and again, I'm using my left hand because the camera acts as a mirror, but right hand rules, you need to use your right hand. I'm going to orient my fingers, which represent the velocity, going downward. My palm here is the magnetic field, which needs to be pointing toward me, and my thumb is the direction of the force. And we can see that my thumb is oriented to the left, or in the negative X direction. So my force is to the left. One note, and I've mentioned this in some of the other videos, but I want to mention it again. One good tip for helping to solve these problems is remember that each of my three components, my force, my magnetic field, and my velocity, all have to be on their own axis. I have my x-axis, my y-axis, and my z-axis. My force has to be on one of those, the magnetic field has to be on another, and the velocity has to be on the third. I can't have two of them on the same axis. So because I know in this problem that my magnetic field is occupying the z-axis, that my velocity is occupying the y-axis, automatically I know that my force has to be along the x-axis. I just need to determine if it's going to be positive or negative, and that's what I need to use the right-hand rule for. Problem 7. An electron, which has a mass of 9.1 times 10 to the minus 31 kilograms, traveling south at a constant speed of 5.0 times 10 to the 6th meters per second, enters a region where the downward component of the Earth's magnetic field is 3.5 times 10 to the minus 5th Tesla. What is the magnitude of the acceleration of the electron at this instant? So before you say, holy polar opposites, Mr. Tiesler, how do we solve for acceleration? We've never done that in these types of problems before. Let's take a look and see what we are given to work with. We are given the charge, because I know it's an electron. I know that the charge is going to be 1.6 times 10 to the minus 19th coulombs. I know the mass of an electron is 9.1 times 10 to the minus 31 kilograms. I know the velocity is 5.0 times 10 to the 6th meters per second, and the magnetic field is 3.5 times 10 to the minus 5th Tesla. Now I'm looking for the acceleration. None of the formulas that we've given you have acceleration in them. But given the charge, the velocity, and the magnetic field, I can find the force acting on the electron. And if I know the force acting on the electron, and I know the electron's mass, I can use Newton's second law to find the acceleration. So first, let's find the force. I know the force is going to equal QVB, the charge, times the velocity, times the magnetic field. So I plug those into my problem, and I am going to get a force of 2.8 times 10 to the minus 17th newtons. I know that my mass is 9.1 times 10 to the minus 31 kilograms, and the force is equal to the mass times the acceleration, according to Newton's second law. So to solve that for acceleration, I divide the force by the mass, and when I do that, I'm going to get an acceleration of the electron of 3.1 times 10 to the 13th meters per second squared. Problem 8. A 0.90 meter long wire carrying a current of 50.0 amps is oriented at 90 degrees to a uniform magnetic field of 0.35 Tesla. What is the magnetic force on the wire? Well, I'm given the length of the wire at 0.9 meters. I'm given the current at 50.0 amps, and I'm given the magnetic field of 0.35 Tesla, and I am looking for the force. I know to find the force, I need to multiply the current times the length of the wire times the magnetic field, F equals ILB. I plug my known values into that equation, and I'm going to get a force of 16 newtons. Note in this problem, I didn't put the sign of theta in there. I could have put F equals ILB sine theta, but I know that the sine of 90 degrees is 1. So that's not going to change the magnitude of my force at all. I'd just be multiplying the product of ILB times 1, and that doesn't change it. So I just left it out in this particular problem just to make it simple. And if everything is perpendicular or at right angles to each other, we don't need to worry about the sign of the angle, because the sine of 90 is always going to equal 1. Number 9. A 0.15 Newton force acts on a 0.40 meter wire as a result of it being located in a 0.020 Tesla perpendicularly oriented magnetic field. What is the electric current through the wire? So I am given the force of 0.15 newtons. I am given the length of the wire as 0.40 meters. Given the magnitude of the magnetic field of 0.020 Tesla, and I'm being asked to find the current. To find the current, I need to use F equals ILB. Solving that for I get I equals F divided by LB. I plug in my known values to that equation, and I'm going to get a current of 19 amps. Problem 10, the last problem in this video. If a wire carrying 23 amps of current feels a force of 0.040 newtons when it is located perpendicularly to a 0.14 Tesla magnetic field, what is the length of the wire? So I'm given the current of 23 amps, the force of 0.040 newtons, the magnetic field of 0.14 Tesla, and I'm being asked to solve for length. So once again, I'm going to use F equals ILB. This time around, I am going to solve for L, or for length. And I'm going to have L is going to equal F over I times B. Plugging in my known values is going to give me a length of 1.2 times 10 to the minus second meters.